Hi guys, I'm going to do I think it was number 4. Number 4 was about design. It was not, it's fairly short. It's this one here. So we're being asked what is it? Yeah, it was number 4B. So yeah, design a system using these states. So first thing you're going to do is, yeah, from these states, we get the present state and the next state with regards to X, because X is what determines the next state. So from this state diagram, okay, yeah, I got this. Sorry for this small handwriting. Yeah, but I got this. So S0 goes to S0 and X is 0, and goes to S1 and X is 1. So after drawing this, usually the first thing we do is to see if we can simplify this. But in this case, we can't simplify because there are no same states. There's no change in states which are the same. I don't know if you understand. Which are the same. Like for example, if S2 was going to S3 and S1, and also S3 was going to S3 and S1, we just cancel all of this and have these three states, which will just simplify the equation. But in this case, we couldn't do that. Yeah, from there, I use the characteristic or table for the D flip-flops. I chose to use D flip-flops because we're being told to use a PAL 16R4, and the PAL 16R4 usually has 4D flip-flops uko mwisho, so ingekuwa easier kutumia hiyo. Could have used something else, but I don't know how you could have done it. So I did that. This filled it in from here. I use this data to I plugged it here, and I got my what? I got these final answers for the D inputs. I got D1 is the sum of all of 4 and 6, because it just appears 1 here. And for D not D0, I got 1, 2, 3, 4, 5, and 7. But I saw someone else got something different here. So here, when you're going through the question, just check what you get here. But I think mine is correct. The other one must have been wrong. Then from here, I went and did the Kano map, and from the Kano map, I got 1, 2, 3, 4. I got 4 groups for D1, then just a single group for D notes, which is this one here. So for D1, I got this pair, I got this pair, I got this one here, and this one. Yeah, then I got this one. So those are 4 different pairs. I wrote down the equation for D1, which is this, and also for D note, which is this. And from here is where, having the equations, now you're going to use the sheet, this one, this sheet. The first thing I did is I identified which flip-flops I'm going to use. So I chose this as my first flip-flop D1, and this one as D note. Okay, this is the first one, then this is the second one. And then in this case, I didn't want to use the clock as my X because I saw the clock just only powers this flip-flops. It has no connection to the matrix, to the graph part of the sheet. Yeah, so I chose my X as pin 6. Then there are some things you also told us to be doing when we were trying to draw this. When you were trying to draw using the PAL 16R4. So the D flip-flop D1 is pin 17. From here, pin 17. The D note is pin what's that? Pin 16. Then the X is pin 6. Then we have also OE, which you told us to always be grounding to power. I don't know if it's I don't have the explanation for that, but if someone has, you can write it in the chat. So you're supposed to ground this whenever you are using this, which is pin 11, and also indicate that the clock is pin 1. So you just write that information somewhere. Then I also from the equations we can identify Q1 and Q naught. So Q1 is the output from this D flip-flop, which comes here. Also, it's here. So which comes here and goes back into the grid. So it comes here, it's bad and it's okay, it's bad or negated and something, and we also have the Q1 bar and the Q now here because this is an inverter. This part here. So this Q bar, which is bad again, becomes just Q, which is position what? Position which is position it's here. So from here we come to position 11. It's also good to number these things because these are you'll have to use this to describe the position for the grid. So it's 0 to 3. Let's count these lines: 3 to 4, 8 to 11, 12 to 15, 16 to 19, 20 to 23, 24 to 27, 28 to 31. So you'll have to have these numbers because that's how we taught us to interpret this grid for you to give our allocation. So we've identified that our Q is position 11. Okay, I don't know position if it's the right word, but it's this 11th line, and Q bar will be the 10th line because this is Q1 bar will be the 10th line, which is this. Then you do the same for the D note, the D note flip flop. You get the Q, which is this, which is going to be position 15, and the Q bar, which is going to be position 14. You have that information, just write it down somewhere and it's how, for example, I wrote mine here, and I also wrote down this information here. Now for us to give an answer, we have to go and look at our equations. For example, D naught, which I did here, it's 6 and 4. And what is 6 and 4? 6 and 4 is Q1 and Q bar from the Carnot map. When you deduce it, you get this. When you come to your grid, and since we already, okay, let's start with X because it's more direct. X, we allocated pin 6, but on the grid it's position. Pin 6 can power these two lines. This is line 16 and line 17. So line 16 is X, line 17 is X bar. So in this case, for the equation, for the D naught equation, we are looking for X bar and Q1, which goes to power this flip-flop. So so what happens? Going to power this D naught flip-flop. So when you're going to I don't know, let me to plot this, we're going to consider the grid that has the AND gates which power the OR gate for this, for the D naught flip-flop. So we're going to use this grid between 24 and 31. So you can just select any point for this grid. But I don't know why he recommended. Okay, let's just use the one from the bottom. So we're going to use 30 for this grid. So you go where your X bar is. Your X bar is, we said our X bar is number 16. So you write 16 and 30. That's your position for X bar. So X bar is 17. The X bar is 17. So you write 17 and 30 is your X bar position. Then we're going to find for Q1. Q1, it's the output from this flip-flop. The output from this flip-flop, so we know that Q1, it's going to be the bar of, since the output is Q, it's Q1 bar, it's going to be the bar of bar Q1. So it's going to be this one here. You go look for the position we put in, we're seeing it's position 11. Then since it's a Q1 and for this grid from 30 to 34, and since we said it's going to be at 30 here, hope you can see, we're going to mark a spot. We're going to cross it. Yeah, this one, we're going to indicate that this is the fuse here. We're fusing here and we're fusing here, so that this line which goes to this AND gate, then this OR gate, then D note, it's going to be a Q and an X bar. I think that's understood from there. So when you're writing the positions, you start with the. Is that a question?
Yeah, there's a question. I will go back to your presentation.
Okay.
Because I just want to understand the procedure
Yeah.
here, yeah. So okay.
Sorry.
I just want to understand the steps you're going to follow, yeah. So okay, I understand.
Yeah.
The point where we use the kind of maps to get our denote.
Now you're getting the. Yeah.
Yeah, I've understood.
Then you're going to select.
And then yeah,
to get up to here, you select the pins. Yeah.
Yeah, selecting was okay.
Then, then you're going to.
So you said for X, you can choose any pin.
Yeah, you can choose any pin for X, any pin, but for the D flip-flops, they've already the pins are located for them here. This four.
Okay. And then you said you chose So the first one. I
chose mine as pin 6.
Yeah, okay. X is
you can choose any. Yeah.
X is okay. So for D, you've seen chosen the first one as E and Niko Juna and Niko Chini.
Yeah, so this is D1 and D note, yeah.
Yeah. Let's just do D1. So for D1,
we're starting with D note because it's slightly simpler. You're just fusing two spots here and here, because the equation for D note is X. It's X bar Q1, which is just this fusing these 2 points. Now for D1, it has a lot of.
Before you go further, just hapo kwa D note.
Yeah.
You've said you're joining your. It was X note now. Q.
You fuse. The word is called, I think, fusing, according to me.
Fusing.
Yeah.
It was X bar. I'm not so sure what the.
Yeah, it was X bar.
X
bar and Q1.
Okay. X bar is here. Okay, here iko sawa.
X bar is here. Then Q1, it's coming from this flip-flop.
Okay.
So you're going to get, So the Q1, the position is over here. So you get where it's here, the Q1.
Yeah.
Then you find its number, because we're going to use this number grid to determine the position for this. So for Q1, which is this line here, you follow it. Yeah, you get to 11. So you're going to have to let's see, we're trying to power this flip-flop.
Yeah.
So this flip-flop will be, the input will be determined by Q1 and X bar.
Okay.
We need to fuse these two positions for a grid which powers this D note, and the grid which powers this D note is from 22 to 31. So just select any line here, because they'll go to an AND gate, any line, but they have to be the same line, because these are different AND gates. If you select two separate lines, you'll be ORing this, then you're ORing it again, which won't give us the desired input for D note. So I selected line 30. This one, just one from the bottom, line 30. So this is where I fused my Q1 here.
Yeah.
And my X bar. Yeah.
And then you do the same for D1.
Yeah, and then you do the same for D1. For D1, it has a lot of components. It has a lot of equations. This one, sorry, I didn't flip this. It has a lot of what? Yeah, it has a lot of different combinations for us to get to D1. We have Q1 and Q naught, Q1 and X, Q naught bar and X, Q1, so it has all of this. So from here, since we have this, the reason why we noted this down, it's also to avoid confusion and stuff like that. So since we have the position for Q1 as this and the position for Q naught as this, okay, you can also write down the position for Q1 bar and the position for Q naught bar, but they're I think 10 and 6. So I think 10 and There's something. Yeah, there's something. I don't want to just give the wrong information. So let's do for I'll just do for one because of time. Let me do for x1, x naught, and sorry, for q1, x naught, q1, q naught, and x bar, all of them. So we're going to have to identify the positions for x bar, which we got as x bar will be 17, because this the first line here is 16, so the next one is 17 where the x bar is. For the q naught bar, it will be this line here, which is 14. And also for the q1 bar, it's going to be this line here, which is 10. Is it 10? Yeah, it's 10. So you have your position as 10 for the x1, for the q1 bar. You have your position as 14 for the x naught bar, and you have a position as what, as this is 17 for the x bar. So, and we are going to power d1. So for this case, I'm sorry, this place is kidogo, not that visible, but for that particular what's it called? I don't have the name. The connection where we get d naught from q1 bar, q naught bar, and x bar. I chose to use line 16 because we are adding the q to get, because we're adding those three fuses. We're adding I don't, sorry, English kidogo. So I chose to use line 16 from q1 bar, which we got it as this. The position was what? I keep forgetting. So the position was 10. Was it 10? Yeah, it was 10. So I took 10 and I fused it here. That's for my q1 bar. For q naught bar, the position was, it's here. I think it's 14 or something. Yeah, it's 14. So for the q naught bar, I took the position and fused it. Got this line 16 bar because we're fusing this line, did I fuse for the x bar? For the x bar, which is this, which is, yeah, 17. I also, I theoretically fused it here also. So you'll have to fuse this, and let's say here, since this is the position for 17, to get this combination, this one here, combination of inputs that gives the input d1. So we just do the same for q naught bar and x, q1 and x, q1 and q naught. It's just the same procedure for Zote, and just put the x's. He's the one who's going to print it, but yeah, that's the. I'm not sure if this is how you represent your final. Sorry, if this is how you represent your final d1, because you can't put the pluses here. So I just did a small bracket to give the location for the q1 or q or x. Then I closed it to mean that this is a single line fused. This is another line being fused. This is another line being fused. This is another line being fused. Yeah, that's how I approached it. But once you get to this point, it's just noting down the pins, all the pins which you're going to use to avoid confusion. Then noting down the equations with the pins instead of this. Noting down the equations. After you finish one, go and draw it. After you finish the next, if this not exactly the entire equation, just like one part of the equation. For example, this, when you get the positions, go and draw it. This, when you get the positions, go and draw it. This, when you get the positions, go and draw it, to avoid being confused. Yeah, so that's the work. Is there any other question? No, there's no other question. So I think I'm good. Bill.
Bill.
Oh, okay.
It's Bill.
Yeah, you had. Can you hear me? And
Yes, I can hear you, Bill.
okay, so the question is, The question I'm presenting was the one that was telling us. The statement is simple. It's that you're given. Wait, can you see my screen? Yeah, I think you can see it. Why not? The question is you're given two ROMs, and then you're told to check whether they have the same, what we call content, what we call data. And you want to check that the output, and what is stored in the ROMs is the same for everything. Yeah? And the ROMs you've been given are 1K by 8. This means that they have 1024 memory locations, and then output lines are 8. Yeah? We recall this from the presentations of last time. I hope we recall. Yeah, I think
Yes.
we recall.
Yes.
Recollection. Anyway, so like this, how I was thinking of solving it is that there are like 3 parts to this problem. And I think I discussed with Celestine and also with Kamara and then also with Gennaro. So I've discussed with 3 people and there are 3 parts. But we didn't discuss one part with one person and then the other part. Like we discussed all 3 parts with all 3 people. Anyway, the first part is comparing the values. I have the solution somewhere, but I don't think the solution will be like my solution looks like this, but I think it requires to be explained a bit before the, and I'm going to come to it. Let me just outline the parts. Comparing the outputs of the 2 ROMs. Yeah. So this is, let's say, ROM 1, and then here we have ROM 2. We want to compare the outputs. And comparison is done very quickly using a magnitude comparator. Okay, in case you've forgotten maybe how a magnitude comparator looks like, it looks something like this. There are 3 control lines, that's less than, equal to, and greater than. And then there are 3 output lines, that's less than, equal to, and greater than. What happens basically, if the less than control line is on, the output will always be less than. If the greater than control line is set high, the output will always be greater than. And lastly, if the equal to control line is set high, what happens is we will compare what's in ROM 1 and what's in ROM 2. So if you set the magnitude comparator to have high as the equal to comparison, and then less than and greater than, you ground them, what's going to happen is you're going to compare the content in ROM 1 and the content in ROM 2. And then if it's different, then it's going to give us a false. If they're the same, it's going to give us a true. I think that makes sense, yeah? I think it makes sense. Is there any question? Okay, maybe there is no question. The second part was making it a bit automatic. So like here, like just with the magnitude comparator, you can compare all the contents and get an accurate, but the thing is, you want to compare all of them. Like you aren't just comparing one memory location at a time. You want to compare all 1024 memory locations, all 1K memory locations. So you want to make this process a bit seamless, yeah? Like we want to make it a bit automatic so that it's not you who has to go memory set in 0001 with your wires and your, that thing, what was it called? Wow, it's been long since labs. Power supply. No, there was a cool name, something Rosebud. Primrose? I think it was Primrose. Anyway, so that you aren't the one who's doing that with your wires going through all the memory locations. We want to make it a bit more automatic. And something that can help us make it automatic is using a counter that counts up to 1024. We know those things, what we used to call them, something like modulo 1024 counter. Those ones, we had done them in the previous semester. Modulo X counter, like it counts from 0 till X minus 1, and then it goes back to 0 and counts again till X minus 1. So now we want such a counter, yeah? We want it to automatically, we want it to take us from 0 till 1024. Okay, for my choice, I chose to use because I don't know whether counters come in black boxes. Like you see the way the ROMs come in black boxes and like these ones, I'm sure they look something like this. But then for the counters, maybe somebody can check the notes and confirm for me, but I'm not too sure they come. So I wanted to use a synchronous counter. You know the two types of counters, asynchronous and synchronous. Asynchronous, we have different clocks. And then synchronous, we have the same clock. The reason I wanted to use synchronous counter with the article "a" before, not asynchronous. The reason I wanted to use the synchronous counter, the 1024 modulo 1024 synchronous counter, will be apparent in a short while. So basically, the synchronous counter usually has a combinational logic circuit to it, and then some JK flip-flops. Also, the reason I wanted to use JK will come soon enough. It has combinational logic circuit and JK flip-flops. So the outputs of these JK flip-flops are the ones which are going to put into our ROM chips, our ROM devices, our ROM memory chips. No, our ROM chips are the ones which we are going to put into our ROM chips. And then, since they are going to be the same, so we are going to look at the same memory location for ROM 1, then the same memory location for ROM 2, then we keep going until the last memory location. Yeah, that's basically the automating part. Is there any question about that part?
If we repeat again what you said there.
The automating part.
The JK flip-flops, why are you using them?
Oh, why I'm using them? It will come in the next part, the stopping part. Oh, we haven't even introduced the next part. What? Sorry for the spoiler. Yes, Gennaro?
Oh, I have a question for
Yeah.
why you used all those flip-flops.
Yeah?
Yeah, the reason we're using the flip-flops is just to change the address, you know.
Yeah?
And from the address decoding,
Yeah?
for a 10-bit, for what is it, an 8-bit? Yeah, for the inputs from the CL combinational logic circuit.
Yeah?
So we have the addresses will only be located in the first 2 bits, the Q0 and the Q1. So the flip-flops are just supposed to go to those 2 addresses because that's what we're changing to get
Why?
different addresses for the ROM. If you put your flip-flops for everything, you'll be changing the data which you're inputting. But we don't want to change the data, we just want to change the addresses. Remember from address decoding, the way we were locating,
But
we
where
were
are we
dividing.
changing the data? Sorry, where are we changing the data?
We're not supposed to change the data, but when you use the flip-flops,
Yeah?
when you use all those flip-flops, you're going to be changing both the addresses and the data.
No, I'm not going to be changing the data, only the address.
The address is only located in the first 2 pins, the Q0 and the Q1. The rest, it's the data.
Q0 and Q1. Oh, these
Yeah.
flip-flops are for part of the counter. They aren't part of the ROMs. These flip-flops are basically the counters.
Oh, so
Wait, am I not? I think I'm not understanding you. Like this?
uh-huh.
Yeah, please come again.
When you're inputting data into the ROM,
Yeah. Oh no, I'm not inputting.
let's just say you're inputting from the knowledge of address decoding.
Mm-hmm.
We only considered the first 2 bits as the address. Do you remember from address decoding, from the way he taught us, we're only considering the first 2, the Q0 and Q1 as the addresses. The rest, let me
Wait,
just put
I
in
think
quotes,
I'm not
it's the data.
getting it. We're only considering Q0 and Q1.
Yeah, as the address. You remember from address decoding, like I think the last topic, yeah, around the last topic.
Let me check. Wow.
It's okay. It's okay. I've understood. Sorry, I was on.
It's not what I'm talking about.
Yeah, I was confused. Sorry.
Oh, okay. I've not gotten your question yet, but
Yeah.
you got what I'm talking about. Okay. Anyway, let's try Fiona's question. Fiona is asking why we're using the JK flip-flops. Anyway, the last part of this thing was stopping. S T O P. Yeah, we want it to stop when we get to the memory address that has different. Because, like, think about it, if it keeps on going, then it will keep on going forever, counting from 0 to 1023, then coming back, counting from 0 to 1023, then coming back, counting from 0 to 1023. And then when you come to check, it might be comparing the memory addresses that have the same data. So you'll think it has the same content, but really it doesn't have the same content. So we want, once we get to...
Hi, Bill.
Yeah?
Break, please. Break.
Oh, anyway, what was the last thing you
You're
said?
breaking. Or it's me. I don't
I
know.
think it's me.
You're very much breaking. I don't know. Someone can confirm unless maybe now.
Am I alone? Am I breaking? Am I breaking?
No.
Oh, I'm not breaking. Fiona, maybe it might be you. Fiona, am I still there?
Okay, sawa basi endelea. But I've not even heard what you said, but so endelea.
Okay, maybe I can come back from where you got lost me.
You were saying the third step was stopping.
Yeah, we want it to stop. Yeah, actually, that's where I am.
So what were you saying about stopping?
Like, if we don't stop, we'll keep counting from 0 to 1023, then from 0 to 1023 again and again and again forever. And if we do that, then when you come to look at the result, you might find that it's the same, but really it's just counting continuously and you've just found it at a memory location that's the same. It doesn't mean that it's the same. Is it making sense? Yeah, am I making sense? Okay, thank you. Thank you. Anyway, so to do that stopping, the inputs of the JK flip-flop, instead of, oh, this is why I was using the JK flip-flop. No, remember from the something table of a JK flip-flop, when you have 0 as J and 0 as K, our next state will be our previous state. I'm not thinking about the other. I'm not writing them. It takes me too long to write. Anyway, when we have 0 as J and 0 as K, our next state will be our previous state. And that's what we want to do. We want to make sure that when our output is that they are not the same, our next state is our previous state and we stay in that state forever. And how do we do that? Because when our outputs are different, remember that the equal sign is going to be low. So that low sign, we come and AND it with the result from the combinational logic circuit. And when we do that ANDing, both J and K will be 0. So now we are going to have 0, 0 as the inputs of the JK flip-flop. That means that our next state will be our previous state, and whatever memory location we were at, we will stay there forever until maybe you disconnect. Yeah, and that's the solution I was thinking of doing. Oh, and why I was using a synchronous counter instead of asynchronous, why I was using the counter that is synchronous, why I chose to use a counter which is synchronous instead of a counter that is asynchronous is, so because if we were using the synchronous counter, one is that the clocking is determined by the other, what's it called? The other counter. So like while you're setting the previous state to be the next state, what might happen? I was thinking something bad will happen if I choose to use a synchronous counter. There was something bad that I had thought about. I've just forgotten about it. Yeah, but that's basically my solution. I'm, let's say, 65% sure because of this part for, not 65, let's say, 57. Yeah, 57% sure because of, no, 57 is wrong. Let's say 50. No, I'm above 50. Let's say 53. Yeah, 53% is better. I'm off 50 because of this part of the combination of the counter that is synchronous. Like, I'm not sure if there's a black box that I can use instead of this. And because of that, I'm going to have to do explanations for this. But otherwise, I'm a bit sure about the procedure. Yeah, let's say 51%. Yeah?
What have you said about those AND gates?
The
You
AND,
yeah, what have you said about that?
oh, I broke again. Anyway, the AND gates are used for stopping. Like, because we know that when the output here is not the same, like when the two ROMs have different input data, different data being output, the magnitude comparator's equal sign will be off. It will either be greater than, because one of them will either be greater than or less than the other. So equal for sure will be off. Now, if equal is off, and then I AND it with the inputs of the JK flip-flop, it guarantees me that I'm going to have zeros as the inputs to the JK flip-flops. Now, if the inputs to the JK flip-flops are 0, it means that our next state is going to be the same as our previous state. Now, if our next state is the same as our previous state, we're going to remain where we are. And when you come and check, you're going to find that the output is 0. Does that make sense?
Yes.
Oh, there are questions. Sorry, I didn't hear the questions. Wait, I think Dan's question. Has he answered? Has Gishero answered? Okay, let me start with Dan's question. Would your logic for JK hold? Yeah, it doesn't matter. Like, the thing is, this equal sign is doing what? This equal sign is doing something important. Yeah, this equal sign, like if the values are different, one will be less than and one will be equal to, one will be less than or one will, yeah, for sure. If the values are different, for sure one will be less than. And if one is less than, then we are guaranteed that equal to will be true. Is that making sense? Like if then,
Yes.
I think it's making sense, yeah? If you are, it's making sense. Daniel, have I answered? Tough crowd, tough crowd. Like, maybe I should explain again. If the equal, like the three possibilities. No, there are two possibilities. Either the values are equal to or the values are not equal. If the values are not equal, then if the values are equal, then the equal of this will be high. If the values are not equal, then the equal of this will be low. If the equal of this is high, then the result from the combinational logic circuit will just get to the JK flip-flop straight. If the equal of this is low, then we are going to have zeros as the inputs to the JK flip-flops, which means we are going to remain at the same state. Ah, okay, let me repeat. Let me repeat. I repeat again. Oh, my patterns. Ah, is there anybody still lost with that concept? Okay, next was Gisheru's question. The question says, also count the number of addresses that are similar. Okay, so this is, I've seen a different variant of this question, which is the one I'm answering. The different variant was saying that find the first memory location where they differ. If we're finding the first memory location where they differ, then this is the solution. If we're counting the number of memories that differ, then what we need to do is, instead of this equal sign coming, instead of this equals, like this equal sign, instead of it coming and running these things, instead what we should do is that it should go to another counter. Like from here we go to, yeah, I think it will work like that. We go to another counter. Let's say I think it can be 10 modulo 1024 counter. Or yeah, we just go to another counter, and then this equal sign will be running as the clock for that counter. I haven't fully worked out through those details, but I think it's going to be something in that line. Like we go to another counter, and then the equal sign is running the clock for that counter. So when the equal sign toggles, like when the equal sign toggles, we go to the next count. But then that might require us to be clearing something. Okay, I haven't worked out the details. I'll get back to you. But I think it's something like that. Maybe somebody has worked out those remaining details. And lastly, Sean's question. Yeah, the purpose of the combinational, yeah, that thing, the long combinational logic circuit is because, you know, we want to use a counter. So it's, I was too lazy to do for the something diagram. What's it called? The state table, previous state, next state. Yeah, I was too lazy to do all that. But it's going to be a combinational logic circuit for sure. Because a synchronous counter has a combinational logic circuit and then the flip-flops, the sequential bit. It's what we call melee, or is it those words?
Bill,
Huh?
let's go back to the diagram.
Yeah.
Over there, where you're saying when it will equal, you'll get a zero coming from the magnitude comparator.
When they're not equal.
Yeah.
Yeah.
Why not? Why don't you, when you get that zero,
Yeah.
why don't you NAND it together with the clock pulses to each of your flip-flops so that they stop working, they'll pause at that point, instead of NANDing it to each one of them individually.
I NAND it to the clock.
Yeah.
That's a great
you NAND it to the clock so that it will be given a 1 to each JK flip-flop, then they'll have to stop.
Yeah, that's a great idea, man. I didn't think of that. Thank you. Yeah, you can do that. Instead of coming and doing the ands here, you can do the ands here with the clock.
Yeah.
Because you know, if it's 0 and 1, 0 and clock will always be 0. So then our clock will always be at 0 and we're not going to move. That's a genius idea. And I think it can be used for the whatchamacallit. Yeah, we finished the other question for Gisheru. This equal sign, now for the next part, is that you take it and AND it with you invert it and then you AND it with or you NAND it with the clock of the next counter, of the counter that's counting the number of different locations. And then what will happen is that when that clock, that clock is only going to work when we have a different memory location. Yeah. So when we have a different memory location, we increment the count. Yeah, and then something like that, it keeps going, it keeps going. Yeah, makes sense, guys. Wait, am I making sense? Please ask questions. Yeah, it's making sense. So,
Me, I don't understand, Bill.
which part?
Ebu, go back to what Sean was suggesting.
Yeah, he was saying instead of doing all these ands here, we do the and with the clock.
Okay, such that.
So now what will happen, because equals to is 0, our clock is always, whatever is clocking these flip-flops is always going to be 0. So now we are never going to move on to our next state, because remember the flip-flops are rising edge triggered, yeah? So if our clock is always 0, then we are always at 0, we never have a rising edge, we are never moving on to the next count, to the next memory location.
Oh, okay. So,
Genius idea, because hey, good points.
So if we are going to do it with the clocks, so it's going to be before the synchronous,
Yeah, the synchronous
counter.
counter will remain as it is, and then our equal to sign, we connect it to the clock. Like here, clock, it will be clock, and then an AND gate somewhere here. Clock, and then an AND gate, and then the one input of the AND gate is the clock, the other input of the AND gate is this equal sign.
So where will the output go to? The output of the clock and the AND?
The output of the clock and the AND is what's going to clock these JK flip-flops.
Okay.
Yeah, it was just that. It's a good improvement. Yeah, we can have D flip-flops now. It improves everything. Yeah, we can have a synchronous flip-flop now as well, because we've removed all the requirements for having everything else. We can have an asynchronous counter, I mean. Yeah, it fixes everything and then we are done.
Okay, so to summarize the new improvements.
Yeah?
I have a question. Yeah. Can you just summarize the new improvements you have for this question?
The new improvement.
We've removed, yeah.
Now we don't have all
this.
This part for the combinational logic circuit and JK flip-flop, blah, blah, blah. Remove it. Yeah, you've removed it in your head. Now replace it with counter, whichever counter you want. Replace it with, was Ripple counter doing that? Just replace it with a modulo 1024 counter. Now you have a black box there, some counter, whatever counter, it doesn't matter. That counter is being clocked by CK. Is being clocked by the AND of equal and CK. That's what you're taking it to the clock of the counter. Is that making sense? Like remove, oh, I've touched, remove all this. All this can be replaced now with a black box called counter. 10-bit counter. Remove all this, it's now a black box called 10-bit counter. And then that black box, because a counter has a clock, the clock of that black box is the AND of the equal to and the clock. And the regular clock, the clock for the system. That's the improvement. Is there any question? Final diagram. Okay, Sean, maybe you can send the final diagram. Sean. Okay, Elvis is asking, is it NAND or AND? It depends on your counter. If your counter is rising edge triggered, yeah, if it's triggered on the rising edge, then what you want is what do you want? If it's triggered, if it's rising edge triggered, then you're going to want a NAND gate so that when this 0 comes along, it's going to be at 1, and then we're going to remain at 1 and never have. Wait, no, if it's falling edge triggered, you're going to want a NAND gate so that when the 0 comes along, we're going to stay at 1 forever and we never have a falling edge. If it's rising edge triggered, you're going to want a AND gate so that the 0 comes along and then it causes a 0 and then we remain at 0 forever. But yeah, I think there's a way each of them can work. Is that making sense? Yeah, that's what Chebet has answered. But we can make the improvement now based off of Sean's idea. Just remove the dependency of the counter to this magnitude comparator, and then instead this magnitude comparator is controlling another counter, and then things work just fine. It now counts, it's now clocking that other counter. I hope that makes sense. It can be done. Gisheru will do that and send us the solution. Yeah. Is there any other question? Okay, maybe not. The other thing was VHDL. Oh, there's another question. Yes, Gisheru? Yeah, do you have a question or? Okay, maybe no question. Okay, continue. Okay. Are you guys planning on doing the VHDL question? Anyway, VHDL, there's a really nice page. This page 28. It has a nice example that you can use as maybe a template if the question is very easy, because it comes from here. This circuit, and then they implement this circuit with VHDL. That's just what I'm going to do. If he brings a very easy question, I'm just going to do that. But you can look into it instead, and it's also not too complicated. Yeah. Okay. So let me stop presenting.
As Gisheru is typing, Celeste, umeona inaweza tupitisha through ya state diagram ili states ama to design.
No, I think the ones I have tulishafanya nini, tulifanya kwa discussion, I think, because I have one yenye, okay, like you see these questions zenye zinaanza na sijui a digital, you're given a state diagram, yeah, and then you're told to use like either SR or D flip-flops and a bin deck to accomplish, or yeah. So I have that. I have a question on TTL calculations. and calculating power dissipation. And I think nyi watu si mmeelewa hizo. As in, I don't want to take your time. Na ni vitu mngeelewa if you read on your own. Ama mnaona aje?
Just take us through 1.1. Napenda kuleta ile 3.1, but note last year hakuleta 3.1, so I don't know. Maybe you could take us through the ones for the state diagrams, or
You're
okay. Huh?
You're saying for 3.1?
Sorry?
Are you talking about design questions for 3.1? Hello? Fiona? Hello? Hello? Hey, okay. No. Hello? Hello? Can you guys hear me? Okay.
Yeah.
Okay, so but okay, acha ya 3.1 yenye nilifanya ni yenye iko na nini? Iko na ripple counter. Okay. So let me just present what I have. If you guys want me to do a question on power dissipation, kuna moja hapa nimeona it was in 2008 hata. Okay. So let me present. This core. Okay. So okay. As my nini is loading, the question was saying, with the help of a clocked JK flip-flop and waveforms, explain the working of a 3-bit binary ripple counter with the truth table for clock transitions. Yeah. Sorry. Okay. Sorry, my mnanisikia? Okay, mnanisikia? Sawa. Okay, sawa. Sasa I think it's better. So the question was, with the help of a clocked JK flip-flop and waveforms, explain the working of a 3-bit ripple counter. Okay, a ripple counter, it will count normally, but now we were saying it is an asynchronous counter. So it does not have one master clock. So if I'm using JK, okay, yeah. Tumezoea kutumia T flip-flop for counters. But now if I want to change JK to T, then I'll short the J and K inputs. No maana I've taken them both to 1. So, because it's an asynchronous counter, now the first one here, the least significant bit, itakuwa na clock yake. But the next one, clock yake itachukua from Q0 here, the previous one. So this is what they mean by asynchronous. It means the clock comes from the Q bar of the previous flip-flop. If it was
Celeste,
yeah.
are you presenting?
Sorry?
Are you presenting?
Yeah, I'm presenting. I am actually using my camera. Can you guys see?
Okay, I can't see, but I'm not sure if it's a problem on my part.
No, I can see clearly.
Unless you could check your connection, Elizabeth.
Okay, now I can see.
Okay, sawa. Sawa. So this one will count normally. So we're saying from 0 to 1, it's 1 clock. And then, yeah, so it's a 3-bit triple counter. So it will count from 0 to 7. And then now, inaisha hapo. So it won't count this 8th one. So if you're told to draw the waveforms, it's like you'll use this table to draw your waveforms. So utakuja uchore 1, 2, 3 hadi 7. Okay, nilifika 6. So nilichora clock yangu 1, 2, 3, 4, 5, 6. And then for Q naught, I was using positive edge triggering. So for Q naught, ndio hii, I know, okay, tunaanzia 0 and then 1. It will count 1 when we, yeah. So the first clock ndio hii 1, tunaanzia 0 and then on the positive edge, it is triggered. So positive edge triggering. And then it goes from 0 to 1 and then at 2 it goes to 0. Okay, I'm explaining well. Yeah, so at 2 it is 0, so tunaona itakuja ishuke, then tena at 3 it's like 0 1 0 1, so it's like 0 1 0 1 0 1. So that's what's going on, and it's the same way you'll draw the next one, because you'll start from 0 for Q1, 0 and then 1 on 2. So tunajua kwa 2 tuko na positive edge triggering on the second count ya Q1. So hapa kwa Q1 on the second count, this is the first count. On the second count, yeah, I've not drawn it so well, but on the second count I should be having my, yeah, then it sustains for 2 and 3, it sustains and then inashuka. So that is how you draw a ripple counter. There was a question I saw, yeah, the same though, yenye inasema how many 32K by 8 RAM chips are needed to provide a memory capacity of 256 bytes. So this is 256K, this is 32K by 8 RAM. So from here and here, I know I'll need 8 chips because it's 256 divided by 32K. How many lines of the address must be used to access 256 bytes? Hii utafanya tu 256 times 1024 because it's 256K, and then you find 2 raised to power what gives you this product. So it's 18 lines on the 256 kilobytes. So note that. How many of these lines are connected to the address inputs of all chips? So for all chips, you're talking about this 8. And because we're using 32K by 8 chips, we're going to find, tunataka tutafute the address lines that we're using for 32K. So this is 32 times 1024. And then the product is the same as 2 raised to power 15. So it's like we're using 15 pins per chip. And then we're using 18 address lines for the memory you want to create. Okay, so how many lines must be decoded for the chip select inputs? So the lines that will be decoded, itakuwa hii 18 minus 15 for you to get 3 lines. And then select the size of the decoder. Yeah, so your decoder will be 3 by 8. So this is a good question. I've seen it, I think 2017. So I'll take pictures and then I'll send to the group. Okay, so let me see. Okay, I think Nigel went through this one, so I won't go through it. I hope you guys understood transmission gates. Ama, do I go through transmission gates?
Yeah, PTR to transmission gets by the PTR.
Okay. So, sorry, let me just find the page. Yeah. So you can be told, using a suitable circuit, give the principles of a CMOS transmission gate. So basically, transmission gate is a logic-controlled switch used to achieve logical modules, such as flip-flops. And it consists of PMOS and NMOS. So hii circuit ndio utachora. Yeah, to show. Yeah. So, and for a transmission gate, inputs are either VDD or 0. So you'll see kwa truth table, instead of kutumia 0 na 1, tutatumia VDD na 0. Okay, so you'll note that for P substrate kwa transmission gate, VDD is held at logic 1, na kwa NMOS it is held at ground. So I think this is just theory nitawatumia. Let me take you guys through the main things you need to know. Okay. So for example, you can be given such a question and you're told, obtain the logic operation performed by the circuit. So we have a transmission gate here, a transmission gate here. So it means kuna PMOS hapa juu na kuna NMOS. And we know for NMOS to be on, you have to feed a logic 1 to it. Yeah. So that is the first thing you need to know. The second thing you need to know, something that will switch on an NMOS will switch off a PMOS. So if I had 1 inaingishwa kwa NMOS itawaka, but nikiingisha 1 kwa PMOS haitawaka because they're dualities. So ili PMOS iwake nitaingisha 0 hapa. So for your transmission gate to work, there has to be 1 being fed on the NMOS side and 0 being fed on the PMOS side for it to allow this data to go through. So that is how a transmission gate works. So let's look at an example here. So there are 2 inputs. Na venye nimesema inputs for transmission gate are either 0 or VDD. So I did my 0, 0, 0, 1, but hapa natumia VDD, then 1, 0 and 1, 1. So let's analyze transmission gate 1. Let me use a pencil. So for transmission gate 1, tunasema ati kuna A hapa, A ni 0, si ndio, na B ni 0. So A ni 0 na B ni 0. So A ikikuja hapa, 0 itakuwa 1 hapa, because it will be negated. And then 0 will be picked here, so tunajua hapa kutakuwa na 0. Aya, B ni 0, so we'll have a 1 here. Yeah. So the when will be waiting here. And then from here, tunajua tuko na 1. This one will be picked na nditengishwa hapa. So you want to see which one will be on and which one will be off. Let's start with this one. So here tunaona kuna 1 hapa kwa PMOS na kuna 0 kwa NMOS. So automatically this won't even work because already there's a 1 in the PMOS, so your PMOS is off. And if one of them is off, the gate won't work. So this will be off. That's why TG1 was off here. In the second part here, there's a 0 here and there's a 1 here. We know NMOS, it will be turned on by a 1, logic 1, and PMOS will be turned on by a logic 0. So this gate will be open and it will allow the data here to pass through. So kenye tutaona kwa output yetu itakuwa ilikuwa 1 here. So we'll see 1 ama VDD kwa output because this is off and this is on. I'll do one last one. So let's do when A is VDD and B is 0. So when A is VDD, then tukiinvert hapa itakuwa 0. So tutakuwa na 0 hapa pia na tutakuwa na 0 hapa. We've said A is VDD, B is ground. So hapa B ni 0. So tukiinvert hapa itakuwa VDD. So VDD inakuja kuongoja hapa. A was VDD here, so VDD inakuja directly. And this is like logic 1. So if you check in the first gate, then we are seeing there's a 0 in the PMOS side, so the PMOS is on. And there's a VDD or logic 1 on the NMOS side, so NMOS is on, which means this gate will be on. Ndio maana tukapata transmission gate 1 is on when A is VDD and B is 0. So it will allow this data to pass. So B was 0, I believe. Yeah, it will allow 0 to pass. So that is how you will analyze your transmission gate. Do you guys want me to go through this question for TTL yenye iko na power dissipation?
Yes.
So below is a low power TTL NAND gate. So it looks like that. So the first thing you need to remember is which logic family are you dealing with? Because sasa hapa we are dealing with a TTL, like a standard TTL. And we know it is either it's in saturation ama it's cut off. So we know if we are saying a transistor is conducting, inamaanisha it's in saturation. Otherwise, if it's not conducting, it is cut off. So let's see. The logic levels at the output Y. So we are finding the logic levels at output Y if the inputs have logic levels 0.2 for low and 4 for high. So inamaanisha if I want to have a low, like nitaweka 0.2 as my input. If I want a high, I'll put 4. And then we'll also find average power dissipation. HFE, VCSAT is 0.3 here, okay, and so forth. So if I have high input, okay, either A or B or both, yeah, or both are high. Because here we have a NAND gate. Remember, it's a NAND TTL. So tukiwa na 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, not AND. 0, 1, 1, 0. Okay. So if we have high input, so for example, tuseme hapa kwa A, we have high input. And we've seen high input, it's like kuingisha 4. So tuseme tukuna 4 hapa kwa A. Na hata 0 hapa. So 4 ikikuja hapa kwa VB1, what we normally call VB1, we know it will be 4 plus the 0.7 for the conduction of the diode. But now, we normally say 4 plus 0.7, 4.7. Okay, here we weren't given value for VCC, so I used 5. So I note that for me to be able to take T2, T3, and this diode here, D3, we normally have here, into conduction, then having a high here will enable me to take them into conduction because niko na 4.7. So my VB1 will be 0.7, which is the voltage for this to conduct, plus VCE sat. Now remember when nimesema TTL, when it's in conduction, inamaanisha iko in saturation. So it can't be 0.7, it will be 0.75. Tumepewa hapa VBE sat.
Celeste,
Yeah.
can you move your camera higher so we can see the circuit?
Oh, so you can see the circuit.
Okay.
Can you see it now?
Yeah.
So VB1 itakuwa 0.7 for this diode here, plus VBE sat here T2, 0.75, plus VBE sat here T3. So that will be your VB1. And if I calculate, I came and found it's 2.2. Okay. And then, yeah, of course, IE1 will be VCC. I use it as 5 minus VB1 over this resistor. So I think IE1 is easy to find. VB4. The next thing they did in this question, I don't think you have to do it, but you can do it in exam, is to show that T4 and this diode here will not go into conduction. Now, in TTL, we normally say if T3 is conducting, T4 will not conduct. And if T4 is conducting, T3 will not conduct. But now we're saying when the input is high, it will be able to drive T2 and T3 into saturation. And because T3 is in saturation, meaning it's conducting in quotes, then T4 will be off. So basically, they normally want to prove, with the next equation, they want to prove that T4 and D4 will not be able to go into conduction. So how do we prove this? VB4, so V base 4 will be equal to VBE plus VD4 plus VCE3 sat, because now this is in saturation. Don't forget that. So yeah, that is basically the equation I have. So I'll have VB4 is equals to, so VB4 is equals to VBE4 plus VD, okay, this is normally D4 plus VCE3 sat. So, and because you want to see whether this one and this one will go into conduction, we'll take them to one side because hatujui bado. So we have VB4 and VD4. So if I bring this side here, I'll have VB4 minus VCE3 sat is equals to VD4 plus VB. Like this is just now arithmetic. Yeah. And normally I'd find it's, if you go through the working, which is, it's pretty straightforward, you'll find it's 0.7. So this value will not be able to take VB4, transistor 4 and VD4 to conduction. That's why now we'll say they are cut off. So because they are cut off, and this one is in conduction, na hii tunaitanga the pull down transistor if I'm not wrong. So it will pull it down to ground. Yeah. So the output you will see will be VCE3 sat, which is 0.3. Okay, tumeambiwa VCE sat tumie kama 0.3. So that is for high output. For high input. For low input, so let's see. Low input is like nikiingisha 0 na 0 hapa. So my VB1, now first, my VB1 would be 0, but hapa low tuliamba tutumie 0.2. So it will be 0.2 plus conduction ya hapa, which is 0.7. So this is 0.9. But if you note, this VB1 will not be able to drive this diode, this transistor, and this transistor into conduction or saturation, because here you will need 0.75, here you'll need 0.75, here you'll need 0.7. So in total, you'll need 2.2 volts to drive these three into conduction, but you have 0.9. So they won't go into conduction, which means they'll be cut off. They'll be off. So T2 and T3 will be off. And if this one is off, inamaanisha T4 ina conduct. So, yeah. So, hapa kulikuwa na mambo kidogo. So not enough to take T2 and T3 into conduction, that one I've explained. So T4 is in conduction. If output is open circuit, D4 and T4 will not have if the output here it's open circuit, they normally say D4 and T4 will not have, will have cut-in voltage. Hii bado sijasoma vizuri, but just know. Mwenye anajua atatuexplainia. So V output tutaona hapa itakuwa VB4 minus cut-in ya T4. Minus cut-in ya V out tutaona hapa itakuwa VB4 minus curtain ya hapa minus curtain ya diode, na tuliambiwa curtain voltage is 0.65. So yeah, this one, yeah, go through it again because I still have stars there. A high value of IL causes T4 to saturate. So we'll have two paths, and I labeled them in my diagram. So path 1 ni yenye itakuja itupeleke hivi, na path 2 itakuja itupeleke hivi. The reason why you're using two paths is so that you can be able to find the value of IL, if I'm not wrong, yeah, IL. So we'll have VCC is equals to, let me start with this. Yeah, VCC is equals to IB, so IB4 times RC 2, yeah, because this one is not conducting, this is off, yeah, so this is the only path it will follow. So IB4 RC2, then we'll have VBE sat, VBE4 sat because T4 is in conduction, VD, and then V out. Yeah, so that is the first part. The second part tutaenda tu straight hivi, tuseme VCC will be equal to IL, so current here is IL, I load, times RC 4, and then VCE sat VD4 plus V naught. Yeah. Okay. So yeah, but IB, there's an expression for IB which you normally say it's IL, load current over 1 plus beta. We're given beta, so yeah, you can be able to find what your IB4 is from that. So using these equations, you'll be able to find IL. Yeah. So this expression for IB4 ni basically kenye utaingisha hapa. And then ukishaingisha, you'll make IL the subject and then substitute in your values to find IL. And when you're able to find IL, now you can calculate your V out when you have low input power. So you'll have VCC minus, it's basically something that we wrote here. It's basically what we wrote here. Yeah, this is what you'll calculate. So you'll make V out, V naught, ama V out, the subject of your formula. Yeah. And then if you're keen enough, you'll get 2.7. So you'll get your low is 0.3 and your high is 2.7. So it's a bit of a long question, but especially for the low input side, what if Y is grounded and T3 becomes a short circuit? I saw that question, but I was not so sure how to deal with it. Situne. I still have to go through it again. Yeah. I think you guys, I'll just send, because I feel like these things are pretty much vitu mmesoma. I'll just send to the group what I've done, and then yeah, you counter check on what will help you tomorrow. So I am tired.
Thank you, Celeste. Thank you so much for taking us through that. Thank you, Bill, for taking us through that question, and Gennaro. We really appreciate, guys. Success in your digital paper tomorrow, Mr. Tutapita. Is not allowing these papers. We just have to pass. So